Hi folks, I thought I would repeat today's lecture just today, so don't think I'm going to do this again. Oh, I might, but not this year. Anyway, just wanted to repeat today's lecture because we're so close to the end of the year and attendance is critical, and I feel bad that you probably had good intentions of coming, but the weather had other plans for you, so or the bus driver, or whatever the case may be. So I'm going to do my best to repeat this, and I hope that this flows. Okay, so today what we were looking at, what we started with, was I'll just show you here. There's an example problem in the text, and it's on page 163. And I wanted to go over this example because it's to do with the thermodynamics of mixing of two perfect gases. And I thought that the explanation was good, of course, but I wanted to go over it because there were, if you were going to practice with this, I was trying to read what your questions would be. Certainly I had a question the first time I looked at it. So we did this together in class. But before we got to this question, that is on page 162, 163, and the diagram for which is here on 163, I thought I would do a simpler version. So if you can see here, we've got 3 moles of hydrogen and 1 mole of nitrogen. So I thought let's just start more straightforwardly with equal numbers of moles, and then we'll get to this. So, all right. So what we did was, and I'm going to try and not move this too much. So here's an example of thermodynamics of mixing, and I've got 2 perfect or ideal gases, best kind, and initially I have them, well, let's use another color. Initially I have them in this funny container, looks like a little aquarium, and it has a divider in it that divides this space, 3D space, up into exactly 2 equal parts. Okay, that's my best attempt at a 3D rendering. And on this side, I said that we had 2.0 moles of argon, and we said that it was at 300 Kelvin. And in this compartment, so let me say what this is. This is a movable barrier, but for the moment it's in place until I withdraw it, in which case this whole volume opens and the gases mix. And on this side we had an equal number of moles, and we took the gas neon, so 2 noble gases, obviously non-reacting and perfect, and also at a temperature of 300 Kelvin. And the question was, once we did all this, the question was, what is, gosh, I hope this is in view, yeah, or in focus. The question was, what is the delta G of mixing for this? And we thought, well, it's going to be negative because gases spontaneously mix. And we thought that we would have a look at last day's notes where we came up with this formula, and as I told the class this morning, we're not going to go through that again. Let's just get to that formula. So we have the delta G of mixing is equal to, we had factored out an nRT, yeah, that's fine. The N is there. I did this morning too. That N is there. And open bracket, this is where we had the mole fraction of one gas, but let's call them by name. We have argon and neon. So mole fraction argon times the ln of the mole fraction of argon plus mole fraction of neon, ln mole fraction neon. Okay, and we can calculate this after mixing. So when I move this barrier, take it out, these gases will now occupy, twice the amount of volume that they had initially. But the key here, before I calculate this, the key here, and what makes this different and simpler than the example given, is that not only do I have the same number of moles at the same temperature, but I can therefore deduce that the gases have the same pressure. So the pressure of argon is equal to the pressure of neon before mixing. And the reason for this is because we have the same number of moles at the same temperature, so they're going to occupy the same volume, they're at the same temperature, same number of moles, so they're going to have, therefore, the same pressure. Okay? So when I move over to here then, and let's do that, because it seems like this is just in focus when it's directly underneath. This is the total number of moles, so this is going to be 2 plus 2, or 4 moles. This R value is my 8.3145 joule per kmol, so moles will cancel. And the temperature is 300 Kelvin. The mixing, of course, since they are ideal, is not going to involve any temperature change. The heat of mixing is 0. And I have a 50-50 mole fraction, so it's 0.5. Actually, let me do this up here. That would be 0.5. And again, 0.5. This is 0.5. This is 0.5. Okay. We will find that the delta G of mixing is, when you take the ln of a number less than 1, you end up with a negative. So this is good because negative means it's spontaneous, and we already predicted that the mixing of perfect gases should be a spontaneous process. What did we get? Minus 6916 joules, and then we thought, well, we should trim that back to just 1 sig fig, so it was about minus 7 kilojoules. So that was our heat of mixing, and bringing it all back into view. Okay, for our example that's similar to the one in the book, example 5.2, but let's look at that one now. Okay, so let's get rid of this one. And now let's actually have a closer look at example 5.2 practice in the textbook. So again, I have mixing of 2 perfect gases, and I'm going to redraw my same little diagram because it's the same idea. They are in this container. And I have a partition that's my movable barrier, and it's dividing it into 2 exactly equal spaces. And on this side I have 3 moles of H2 at 298.15 Kelvin. And on this side, exactly the same volume, but only 1 mole, 1.0, of N2, nitrogen, and it is at 298.15 Kelvin as well. So the key here is that before mixing, and after mixing as well, but before mixing, the pressures are not the same. So the pressure of H2 does not equal the pressure of N2. And what I'm going to do is say, let's let the N2 pressure before mixing, because I don't know what these numbers are, computer's going to sleep on me. Let N2 pressure before mixing equal P. There's my variable, P. All right? And if that's the case, and I have 1 mole, and over here I have 3 moles, and everything, the temperature is the same and the volume is the same, then I hope you agree that the pressure before mixing for hydrogen would be 3P. So let's say, therefore, the pressure of H2 before mixing is 3P. Okay? So what I want to do is, again, I want to find delta G of mixing. But I can't plug into the formula. Let's just pull this back for a second. I can't plug into the formula that I did here, and the reason is because I'm not starting with equal pressures, so it's not as straightforward. So you want me to put this kind on the exam, right? Okay, so what do? Well, I revisit the idea that that this delta G of mixing is equal to the total G of the final state minus the total G of the initial state. And my final state is the mixed state, so I'm going to define that over here. And my initial is the unmixed state. Okay? Now my unmixed state, to think back now to our lecture that we did before, and the total G was equal to, let's use the gas name, N, it's going to be NH2 mu H2. Oh shoot. I am not going to get that. So my phone is ringing. Sorry, folks. I'm doing this in my office. Plus, that's H2, plus, whoops, I'm distracted by the phone. Okay. I don't even know who that is.